Okay, everybody. So welcome to our fourth lecture on information engineering. So before we start, somebody asked me a question about the previous homework. So let me comment briefly about it. So there's something about Bayes' theorem, and you had to evaluate probability of y equals to 1. So you were only given conditional probabilities, and you didn't have the complete probability of y equals to 1. So you could complete it by using those individual probabilities and averaging them up. So in other words, what you could have done is you use the probability of y equals to 1 given x equals to 0 times the probability of x equals to 0 plus probability of y equals to 1 given x equals to 1 times the probability of x equals to 1. Right, so in other words, this thing here is like the probability of y equals to 1 comma x equals to 0. And this thing here is probability y equals to 1 and x equals to 0. So essentially, this is like marginalization of over the variable y. So it's the marginal of y actually being computed by adding up the joint probabilities. So this whole thing here is sometimes called the law of total probability. Okay, so whenever you have a problem involving Bayes' theorem where you have probability of x given y is probability of y given x times the probability of x over probability of y. Basically, this thing here is actually probability of y given x times the probability of x, and then you sum over all the possibilities of x. Okay, so is that what you were telling me?
Yes, that is right. I was asking that, and when I computed all that, I got an answer equal to 1, and I don't know if that, because 1 is it's supposed to be less than 1, right? The answer.
Generally, yes, but I don't know. I didn't go look at the solution.
Okay,
But
because
I
the
would
computer
expect it to be less
asked
than
me.
1.
Okay, it should be less than 1.
Yeah, if the numbers are less than 1, then when you add them up, things are still less than 1.
Okay, understood. Okay, thank you.
Right?
Yeah. Thank you.
Any other questions before we start our today's topic?
I thought the intent of that homework was that it was supposed to, the outcome was 1 because it was just a conditional probability. So that was, I guess, what's the outcome? It was like x is equal to 1 given that, or y is equal to 1 given that x is equal to 1. And since it was a z, I don't remember what they call it, the z channel, I guess.
Okay, yeah,
it was
might
always
be,
true.
but it's certainly possible that the solution is 1.
Okay,
But,
Michelle,
but
did
I
you
don't
also
know
get
yet.
1?
Yeah, I did.
Oh, okay, thank you. I was just very confused. Okay, thank you so much.
Mhm. Okay, so let's start with today's topic. We are going to discuss how to quantify information content in random variables and information sources. So up till now, we've seen how do we do error correction codes and how do we decode them. But now we're going towards fundamental limits of how do we represent information and then compute the fundamental limits of channels in terms of capacities. So I'll start with an intuitive explanation of measuring information. So consider an event where a random variable x denotes the direction of sunrise. Okay, so the probability mass function of this variable is as follows. So we have the possibilities x and we have their probabilities. The probability that the random variable takes that value. And in this case, we have for possibilities, could be east, west, north, and south. And the probability densities or the probability mass is as follows. So there's 1, 0, 0, and 0. Okay, so now if I tell you that the sun rose in the east today, there is really no information gained here. I mean, you already knew that. It's a certain event. So there is no information gained. Okay, and the reason is because it's a certain event. But now let's take another example. So consider another event. Y that denotes whether there is a storm or not. Okay, so the probability mass function is as follows. So there is the event, and then there is the probability that y is small y. So the small y can be a yes or a no. And if it is a yes, the probability is 0.01. It's a no, it is 0.99. Okay. So essentially, it's very less likely to have a storm on a particular day. Now, if I tell you that there will be a storm today, it's a useful information for you, right? That can be shared with other people. So there will be a storm today. The information gain is high. Okay, so essentially, if there's uncertainty in a certain event, and if you're able to predict the outcome, there's a lot of information gain. So bottom line, so what we infer from this example is that information content is actually directly proportional to the surprise. Okay, so the amount of surprise you get when you're able to see the outcome of that event. And note that the surprise is actually, and note that surprising events have a low probability. Or surprising event okay, so what we can eventually say is that information content is actually inversely proportional to the probability of that event. Okay. Now, if we have two independent events, let's call them X and Y, right? And note that they are independent. So their information basically content should be the information content in X plus the information content in Y. Okay, that's kind of an intuitive idea. So this sort of property can be satisfied if we use a logarithmic function to define the information content. So that means if you want to find the information content, you can say that the information content in X is actually, or the event that X equals to small x is actually the log of 1 over the probability that x equals to small x. Right, so let's use this definition to define what an information content in a certain event is. So if in case x and y independent, then the information content in the event that x equals to x and y equals to y is actually the log of the inverse probability that x equals to x and y equals to y. But since x and y are independent, right, this can be written as the log of 1 over probability x equals to x times the probability of y equals to y. And from the properties of the log, you can split it up and say this is log of 1 over probability x equals to x plus the log of 1 over the probability y equals to y. And essentially, this is the information content in x, and this is the information content in y. Okay. So any questions so far? All right, so next we will formally define what the information content is from a Shannon point of view. So so they call it the Shannon entropy in honor of Claude Shannon. Right, so this log of the inverse probability is actually also called the entropy. Right, so this term entropy is actually borrowed from thermodynamics. Right, so if you study thermodynamics, they will tell you, the level of disorderliness in a system or the level of, how disorganized a certain system can be measured using the entropy of the system. And the same thing when we apply this to the random variables. So the more surprising or disorderly a random variable is, the more entropy it has. Okay, so Shannon entropy is defined in a similar way that we just mentioned, but it's actually the average over the entire ensemble. So we write down the formal definition here. So it says that if x is, and remember this is limited to discrete random variables. We also have another definition for continuous ones, but it's a little different. So if you talk about discrete random variables with that can take values from a certain set. Let's say that set is chi, and that contains x1, x2, and so on. And assume that there's probabilities for these events in the set. And let's call these probabilities probability x equals xi, and let's call them pi, right? For all I is 1, 2, and so on. Then the entropy is defined as the h of x, which is by definition it's the sum I is 1, 2, and so on, pi log 2. So this is the log 2, and we use the base 2 to represent the information content in bits. So okay, so if you look closely, basically this part here, you know, this is the information, right? And this part really is doing the averaging. So you multiply everything with or each term with its probability, and then you sum it all up. So you get the average kind of information. And in other notation, you can actually just say this is the expected value of the log of 1 over pi, right? And maybe I mean, this can only be written if you consider this as a new random variable, right? So it's consider as a transformed random variable, because its expectation, you know, it's like I mean, there needs to be values, and there needs to be probabilities. So you consider 1 over pi as a transformed variable, and then each of them have the probability pi. So that's the computation of the expectation. And we'll get there with a few examples, and hopefully that will make it clear. Now, before moving on, we'll talk about a few properties of this new term entropy that we have just defined. So if you look at this definition, basically you'll notice that the entropy is always a positive number, right? It's non-negative. So first thing, the h of x is actually non-negative. So if someone comes up to you and tells you the entropy is minus 0.5, that's absolutely not true. If you notice, the entropy is 0 only if x is a deterministic random variable. Okay, and let's do a quick proof here. So if someone tells you that the sum over I of pi log 1 over pi is 0, and because each of these terms are positive, so then for the sum to be 0, all terms must be 0, right? So then all terms must be 0, which means that pi times log of 1 over pi equals 0 for all I. Now, if you have this, then for this product to be 0, either the pi equals to 0, right? So either or the log of 1 over pi equals to 0, right? So if log of 1 over pi equals to 0, that means pi is 1. So therefore, pi equals to 0 or pi equals to 1 for all I, right? And you know that we know that sum of all pi is 1, right? Because it's a probability. So then x must be deterministic. In other words, there is no randomness in x. Okay, so I also want to put a quick comment here that if pi is 0, then pi times log of 1 over pi is actually 0. So it's 0 times log of 1 over 0 is undefined, right? So but limit, or let's say lim x goes to 0, x log 1 over x is 0. So we will consider zero times log of 1 over 0 equals to 0. Okay, so next point here is simply a repetition, which says that Shannon entropy is a measure of surprise. That's a measure of surprise or uncertainty in a random variable. And also referred to the information content. Okay, another property is that the entropy is, or Shannon entropy, is maximum if the random variable is uniformly distributed. Okay, so in other words, if every outcome is equally likely, then that random variable has the highest entropy because you cannot predict anything. Right? There's nothing you can say about it. Anything can happen with the same chance. Or in other words, symbols are equiprobable. Okay, so I can write this as the h of x equals log 2n if di is 1 over n for all I. Okay, so that's kind of a result here. And we can do a quick proof, because if you compute h of x, that's by definition the sum I1 to n pi log 1 over pi. And if all the pi's are 1 over n, then the summation will become I equals to 1 to n 1 over n log 2 of n. And then if you compute the summation, it's just going to be log 2 of n. And for any other random variable, so for general, right? So for any general, apart from the uniformly distributed ones, the h of x is always less than this number, which is log 2n. Okay, again, important result here. So any random variable cannot have entropy higher than log 2 of n. And it is equal to log 2 of n if symbols are equiprobable or we have a uniformly distributed random variable. And again, we can prove this by using the definition of the entropy, which is again I1 to n pi log 1 over pi, which is essentially the expected value of log 1 over pi. Okay, and consider this 1/pi as a new random variable, right? So now notice that log is strictly convex function, right? So it's what that means is basically it's right. So there's a curvature is convex. So by Jensen's inequality, there's an inequality which is called the Jensen's inequality. And that inequality says basically that if a function f is convex, then the expected value of f of x is actually less than the function evaluated at the expected value of x. Okay, so that's the Jensen's inequality. Now, if you go look at this thing here, the log is a convex function. So what we can say is basically h of x, which is the expectation of the log of something, which is 1/pi, is actually less than the log of the expectation of 1/pi. Right, so which is actually equals to so this thing here is actually n, right? So therefore the h of x is less than equals to log 2 of n. Maybe I can write this more explicitly here. So expectation is what? The sum of over I, pi times 1/pi, right? So these cancel, so you're just summing 1 to n, which just turns out to be capital N here. Okay, so these are some very critical and important properties of the entropy function that we have just come across. And now I'll give you some examples of how to compute entropy for simple experiments. So let's take a simple coin toss experiment. So consider a simple or fair coin toss experiment. So what that means is the probability of X being heads or tails is actually the same. So the probability of X equals to, we can call it 0 here, and 1 for tails. And so fair coin, these two are equal, 2.5. Now entropy of such a coin toss or such a experiment is simply by formula, the average. So it's the sum I1 to 2, or we can say 0 to 1. Say X here. Well, I mean, I0 to 1, pi log 1 over pi, right? So the first probability is 0.5 times 1 over 0.5 plus 0.5 times 1 over 0.5, right? So it's so it's so 1 over 0.5 is basically, oh, there's a log here. Oops. Okay, so now 1 over 0.5 is actually 2. So log 2 of 2 is 1. So essentially what you will have is 0.5 plus 0.5, which is 1 bit. So the information content in a fair coin toss is just 1 bit. Now imagine a coin which is biased. So we'll just repeat the same computation with a bias. So a new coin with probability X equals to 0 is 0.25. And then probability X is 1 is 0.75. Now for this coin, the entropy again will be the sum pi log 1 over pi, right? So this is going to be 0.25 log 2, 1 over 0.25 plus 0.75 times log 2 of 1 over 0.75. This turns out to be, this is 2 bits, right? And this is 0.45 bits. So if you compute this average, it's going to be 0.811 bits.
I have a question.
Yes, yes.
How do you get the compute the 2 bits and the 0.5 bits? Is it between the log 2 of?
Yeah. So whenever you take the log 2 of something, you can say that the result is in bits.
But
Hey,
you don't want it to
binary.
be negative because log 2 is -2, right? To the power of -2 is. Oh no! Wait. Okay. I got it. Thank you.
No, log is a function, so it's
Function.
just
Okay, got it.
1 over 0.25 is actually 4.
4. Yeah.
Yeah. So so this is kind of 2 bits, and if you average them, the result is again in bits.
Got it.
Now, oops. So since we know the probabilities of the input, there's actually less, there's less information content or element of surprise.
Sorry,
So
another question. Sorry.
Yeah, yeah.
Why is it log 2? Can it be like log 3? When if it's like log like why is it log 2 again?
Yeah, yeah. So it can be any base of the log, but then the results will be in a different unit. So if you use log E, then the result will be nat.
Okay. So
Right?
since it's bits, bits is like 0 and 1. Is that why it's 2? Because we
Yeah,
have
yeah. So we deliberately use the log base 2 to represent the number or the information in terms of bits.
bits. Okay. So it's always gonna be log 2 for our purpose for this class, right? Because
Yeah,
we're
for
only
this
using.
class, yes.
Okay, got it. Thank you.
I mean, unless we specify it explicitly that you're using a ternary system, something called ternary, it's log base 3,
Okay,
right? So binary, ternary.
got it.
But generally we will use the binary system, so we just use log base 2. Now note that the information content has reduced, right? So information content reduced from 1 bit, which was the information for a fair coin. And this is because the amount of surprise has reduced. Okay. So we know that zeros are more or less likely, right? 0 is less likely. So there's less surprise as compared to the fair coin, because in that case, you don't know what's going to be the outcome. So you have no information about it. But the moment you had some bias in the coin, you have some information about the outcomes. So your surprise has reduced, and essentially the information content is lower. Now, third case, it's a trivial one. So if you consider a deterministic coin, where probability x is 0, is 1, probability x is 1 is 0, then the entropy is essentially 0. So h of x will be the sum of I 0 to 1 pi log 1 over pi, 0 times log 1 over 0 plus 1 times log 1 over 1. We said this term is 0 and then this term is 0. So your information content here is 0 bits. Now, finally, the generic case. So consider you have a Bernoulli random variable. Right? So Bernoulli is like a coin toss experiment, but with a generic probability. So your probability x equals to 0 or 1 is p, and then x, the probability x equals to 0 is 1 minus p. Now the entropy by formula is going to be p times log 2 of 1 over p plus 1 minus p times log 2 of 1 over 1 minus p. Right? You take the probabilities, take the inverse, do the log, and then average it with their corresponding probabilities. Now, the small p can actually be between 0 and 1. So if we plot this type of equation against the variable p, you will find a curve that will help you understand how the entropy changes with the randomness. So this is P, it can be between 0 and 1. Then your oops. So if you go and plot this in MATLAB, you will see that this is the type of curve that you will obtain, and it peaks at 0.5. So if P is 0.5, then you have the maximum entropy. Right, and we computed this was 1 in our first example. Right, that corresponds to a fair coin. And if you go back to our properties, it said that the h of x is always less than the log 2 of n, and n here is 2, right? So it's equals to 1. So we'll say this is because n equals to 2 for Bernoulli. Now, if you look at this graph here, important observation here is that this point here corresponds to a deterministic random variable, right? And this point here also corresponds to a deterministic random variable. Right, and in the case of 0.5, we will have the most randomness. Right, so that's reflected in our entropy. When we have a P which is 0.5, you will have the maximum entropy or maximum level of surprise. But if you are, on either extremes, then your entropy goes to 0. So this kind of measure, which was proposed by Claude Shannon, got really famous because this could display how disorderly a source is or information source is. And I mean, it could actually quantify how much information content is there in the source. How seriously should we take a source? Right, so if there's a source that only generates a very biased amount of content, then it's not a very useful source, or we shouldn't pay much attention to that type of sources. It's only when the information content is really high that we need to take actions and kind of pay more attention towards that type of data. So the first thing that came to widespread application was the idea of compression. So how does the entropy implicate, or how does entropy affect the compression? So the first thing was the entropy measure actually gives the minimum number of bits required to encode an information in the source. Okay, and the second important fact is that the best compression cannot reduce the average length of code words. Any lower than the Shannon entropy of the source. Okay, so essentially, Shannon entropy is kind of the fundamental limit. You cannot do better than that in terms of the number of bits required to represent a certain information source. But we'll see the details later. These are just facts that I want to put up front. But we'll see in today's lecture and perhaps the next one about why do we say that this is the limit and how does this help in computing the capacity of channels. Again, the capacity is kind of the maximum you can do in terms of rate for a zero probability of error. So up till now we saw what the entropy of a random variable is, and now we'll see what something called joint entropy. So let's say there are two random variables. I mean, we actually introduced this in the beginning, but that was just a kind of a casual introduction. So joint entropy idea says that if X and Y are jointly distributed discrete random variables, with the joint probability mass function Pxy of X and Y or xy belonging to a set chi cross y, then the joint entropy of the variable X and Y can be written as the HXY okay, and is defined as the expected value of the log of 1 over the joint probability. Okay, so similar definition, but here basically the joint probability, since it has two random variables, so expectation is actually a double sum over both X and Y. So X belongs to this set, Y belongs to this set, and we have the Pxy times the log base 2 of 1 over Pxy okay, so that's the definition of joint entropy of two random variables. And we can take an example to illustrate how this can be computed. So let's see, let's say there are two random variables. So let X and Y be the binary random variables. With the following probability mass function. Okay, so let's say this is X, this is Y. X can take the value 0 and 1. Y can take again the value 0 and 1. And their joint probabilities are it's 1/2 here, 1/6, 1/6, and then 1/6. Okay, so from this grid, we can come up with the marginal distributions of X and Y. Let's try to write them here. It's so here, if we collapse the Y dimension, we'll have the probability of X equals to X, which is just the sum of the rows. So it comes out to be 2/3 and 1/3. On the other side, if we collapse the X dimension, we'll get Y equals to Y, and sum over the columns, so it's 2/3 and 1/3, right? And if you sum all of them, both the marginals, you will get 1. So this is the marginal PMF of X, and this is really the marginal of Y. Now the joint entropy which is H, X, comma Y, is actually double sum, right? So X from 0 to 1, Y is from 0 to 1. We'll have PXY times log 2, 1/PXY. Okay, so here we have, I mean, three probabilities are the same, so we can actually just, so basically we have to add over all these 4 terms, but 3 of them are the same, so we can just say it's 3 times 1/6 log 2 of 6 plus 1 times half log 2 of 2, right? So this turns out to be, this is 1.29, this is 0.5. So it turns out to be 1.79 bits. Okay, so let's see what the individual entropies are. We have the marginals for both X and Y. So if you want to compute H of X here, it will be, 2/3 log 2 of 3 over 2 plus 1/3 log 2 of 3 comes out to be 0.918. Okay, so similarly, h of y is same thing, right? So it's 1 over 3 log 2 of 3 plus 2 over 3 log 2 of 3 over 2, and it turns out to be 0.9918. So if you look closely, what you'll notice here is that h of x, y is actually bigger than h of x, right? But it's actually less than h of x plus h of y. Let's say if you look at h of xy, it was 1.79. If you add them, it comes up to be 1.83. An individual h of x and h of y are 0.92. Right, so what you see is that the joint entropy is not actually the sum of the two entropies, and this tells you, this piece tells you that or the x and y are not independent. Right? So if they were to be independent, then the joint entropy would have been the sum of the entropies of x and y. But because there is some overlap here, or some dependence between x and y, this is not the case, and we'll see this later as one of the properties of mutual information. The joint entropy. Okay, so we'll do a motivating example here to see how entropies are useful and how joint entropies come into the picture. So,
Hello.
yes.
So since they're not equal to each other, like 1.79 and 1.83, if they are equal to each other, they'll be independent. But since they're not, so they're not independent.
Yeah. So because the sum of the entropies is not equal to the joint entropy, so that means there is some kind of overlap or dependence between x and y.
Okay, got it. Thank you.
I mean, if you take a look at our previous example in the beginning, we said that if from our intuitive example, we said that if x and y are to be independent, then their information contents should be the sum. So that's how we came up with the log function to define entropy.
Okay. So in this case, hx comma y should be equal to hx plus hy in order to be independent.
Yeah,
Okay.
true.
Thank you.
Okay, so let's take a quick look at the motivating example. Okay, so now consider discrete memoryless channel. So this is nothing but an extension of a binary symmetric channel. Or let's say generalization. Okay, so let's say there we are talking about a discrete memory memoryless channel. So what that means is that we consider that there are R different input symbols, and outputs one of S output symbols. Okay, so that means that there's a black box let's call it a DMC, and there are R different inputs. So the first one is 0, 1. Instead of having a binary inputs, we have 0 to R minus 1 different inputs of the variable X. And at the output, we can have S different outputs. So S minus 1. Let's call it Y. So now the reason we call it a discrete and memoryless is it's simple. Discrete comes from the fact that finite number of inputs and outputs, while memoryless implies that the current output only depends on the current input. Okay, so there's no memory in the channel. Whatever you input at the current instant only affects the current output. There is no memory looking back at the previous inputs. Now, for example, the binary symmetric channel, it's an example of DMC. So in a BSC, basically you have discrete inputs, 0 and a 1, and they get mapped to discrete outputs. With probabilities as follows. So your kind of transitions are memoryless. So Y0 only depends on whether X is 0 or not. So it's only the current input that matters. Okay, now H of X here is the, if you look at DMCs, right? So H of X represents the uncertainty So I'm trying to relate the ideas that we have talked about to communication channels or examples that that correspond to communication systems that we've been talking about in this course. So if h of x is the uncertainty in the input and h of y is the uncertainty in the output, and let's say h of x and y is the joint uncertainty in both input and output. So remember, we just like probabilities, we can also, right? So we can also think about uncertainty in the input given the output. So again, the idea of conditional probability is being extended to entropies, calling them the conditional entropies. So we can also ask about the uncertainty in the input given the output, right? That's a more interesting question to ask because we sent some X and we received a Y. So if we received a certain value of Y, what is the uncertainty in X that is remaining? So does the Y help you discover what the original information was sent? Given a certain output. So this can be referred to as the conditional entropy. And referred to as h of x given y. So essentially, if there's a variable x that goes through a channel and get transformed to y, then before observing y, we have uncertainty h of x in x, right? Now, after observing y, so I should have an uncertainty called h of x given y, right? And hopefully h of x given y is actually less than h of x, right? So that's our hope, because having more information can actually reduce your uncertainty about the other random variable. So we will see this a bit later, but let's talk first about what the conditional entropy is. So we've talked about entropies, joint entropies, and now conditional entropy. Now, this is very important to understand. So everybody, please try to pay attention. The conditional entropy is actually the average of h x given y is yk over all outputs yk. Okay, so in other words, h x given y is actually the ensemble average over all h x given y is small y. Right, so it's the average over all conditional entropies. So let's develop this further. This will be ey of y, but then the h of x given y of y equals to y can be computed by using the conditional distribution of x given y. So for all x, we can say the probability x given y log of 1 over probability of x given y. Okay. Now, if you expand this, basically, you can pull out the summation. So the sum over x comes outside. And you will have, right, you'll have these two terms. And these two terms will give you the probability of x comma y log 1 over p x given y. Right? Okay, so essentially, it can be written as the expected value of log 1 over px given y. Right, so it's a conditional density of x given y, and you take the log base 2 and take the expected value with x and y. Right, obviously expected value means multiplying it with the joint density and doing this two summations. So let's take an example of how we can compute this. And I would emphasize again to pay more attention towards this, because this is slightly confusing and maybe it's not straightforward. Okay, so let's take a quick example. So let X be the outcome of rolling a fair die. Right, so that means your outcome space is really 1, 2, 3, 4, 5, 6. And the PI is 1/6 for all I is 1, 2, up till 6. Now let's say let Y equals to 1 if X is less than 2 and 0 otherwise. Right, so you see that the X and Y are dependent, right? They depend on each other. So X is a outcome of a rolling die, and Y is something that depends on what X is. If X is less than 2, less than or equals to 2, it is the Y is 1, otherwise the Y is 0. Now let's see how the table looks like for X and Y. So this is sometimes very confusing for students, but let's try to get through this. So there's X, and it has 6 possibilities. It's 1, 2, 3, 4, 5, and 6. Right, and we have PIs, which are the probabilities. So it's 1/6. Okay, and the Y is actually, Y is dependent. So whenever X is smaller than or equal to 2, it is 1, otherwise it is 0. So I'll say Y is 1 here, it is 1 here, and it is 0 here. Right? So that's the kind of space that we're looking at. I mean, you can always draw another kind of picture, and maybe I should do it because this has always been confusing. So let's say so this is X, this is Y. X is 1, 2, 3, 4, 5, 6. Y can only be 0 or 1. And when X is 1 or 2, right, we have Y is 1, right? So Y cannot be 0 here. Right? I mean, this is it's not possible. And Again, these are not possible, right? So we only have 6 possibilities. So these are, again, 1/6 probabilities. Okay. So what is the probability of y equals to y? It's just the sum of the rows. So you'll have 1/3 and 2/3. Right, hopefully everybody is getting this. And the marginals for x, which is probability x equals to x, is 1/6, 1/6. Okay. Let's get rid of this diagram here. Now, the important part is how do we compute the conditional density? Right, and I'm pretty sure some of you may not have done it, so it's important to understand how do we compute the conditional densities, because eventually we want to go to the conditional entropy. Now, and it has to be the probability of x given y so probability x given y, right? So remember, x given y is a random variable itself. So x given y is 0 is a different random variable, and x given y is 1 is a different random variable. So they can have different densities. So what happens if y is 0? X can be 3, 4, 5, 6, right? So by definition, basically this is probability x comma y equals to 0 divided by probability y equals to 0. Right, that's the definition of joint or the conditional probability. Now this, when y is 0, we look at these cases here. So there's 4 possibilities. When y is 1, you only have 2 possibilities, right? So basically you have to look at the joint value and then divide it by the probability y equal to 0. So this will be 4 different values. So if x equals to 3, x equals to 4, x equals to 5, and then x equals to 6. So if x equal to 3, the joint density is 1/6. That has to be divided by probability y equal to 0, which is 2/3. So we'll get 1/2. So same thing, if x equal to 4, it's the same thing. Right, so we get 1/2. Oops, sorry, this is 1/4 here. And this is actually this is correct, right?
That is correct. Yes.
Yeah.
Flip it over, it becomes 3/2, and then the 3 and the 6 cancels out. So
Yeah.
1/4.
So actually it's the same for all of them, right? So we just Okay, but when we say y equals to 1, basically by definition, this is the joint probability x and y equals to 1 divided by probability y equals to 1. So when y is equals to 1, we just have two cases. So we will have x equals to 1 or x equals to 2. So this time it's going to be 1 over 6 divided by 1 over 3, 1 over 6 divided by 1 over 3. So this is turns out to be just half and half. Okay, now we've got the conditional distributions. So we will get to the h of xy, x given y. So h of x given y, again, very important. This is a bit complicated, but once you go through it, you can understand what's going on. I encourage everybody to try to solve this example again. So h of x given y is actually the average over of all these conditionals, right? So it's 1 over x given y equals to small y. So essentially, we have two values of y here. So it will be y0, right? So forget about it. I mean, we can say y0 to 1, and right here, probability x given y0. Oops, I'm sorry. I think the better way is to use this formulation here. So say, because otherwise it's going to be a little messy. You can always do it. Just say that the h x given y is actually probability of y times h of x given y is equals to small y. Now h of x, which eventually will be probability y0, h of x given y0 plus probability y1, h of x given y equals to 1. So what remains is basically finding h of x given y equals to 0, right? Which is simple because you have the densities. You have density, which is really the expectation of the log of 1 over probability x given y equal to 0. So you have the density. That's this one. So it's 4 times log 2 of, so it's a 1 over 4 times 1 over 4 times log 2 of 4. Okay, and this is 2 bits. And h of x given y equals to 1. It's really the expected value of log 1 over probability x given y equals to 1. So this time we have two values of probability half. So we'll have half log 2 of 2. And that turns out to be 1 bit. Right, so therefore the h x given y is now this thing here. Let's grab it. Okay, so this will be weighted by probability of y equals to 0, which is 2/3. Plus 1/3 times 1. So this is eventually 1.66 bits. That's the conditional entropy. And again, notice important thing, h of x given y, which here is 1.66, is actually less than equals to h of x, which if you compute is going to be log 2 of 6, which is 2.58. Okay, so observing x, observing y actually reduces uncertainty in x. Okay, so just a summary remark here before we move on. So the entropy is computed using a probability mass function. So whatever the x values are doesn't matter. What really matters is the probabilities of the outcomes or events. Probability mass function. So using conditional probability, we probability x given y is y, we get h of x given y equals to y for all values of y, small y. Okay, then we average over all possible of y to get the joint entropy. Right, so that means h of x given y is actually the sum over y of all the h of x given y is equals to small y. Right, so this entropy depends on a probability mass function, and that probability mass function has to be the conditional probability mass function for a small y value. And if you have all the small y values, then you will have different conditional entropies, and in the end you just average them together to get the h of x given y. So this requires a little practice. I mean, you may not get it if you don't do it by yourself. So try the same example without looking at the notes, and you get the hang out of it. Now, I mean, I can keep talking about the conditional density, but let's, or conditional entropy. Let's mention some rules here, or entropy rules. Just like we have laws of probability and probability properties, we can also have some entropy rules. So first one is called the chain rule. So chain rule says if h of x, y, which is the joint entropy, is actually equals to h of x plus h of x given y. So it's the entropy of x plus the remaining entropy in x condition of, oops, this is the y given x. So it's the entropy in x plus the remaining entropy in y. Or it can also be written as the entropy in y, but adding the remaining entropy in x given you observe y. Okay, so these are important results that will help you compute those quantities if you know one, some of them. Now, for two independent random variables, x and y, basically the joint entropy h x y, as we've mentioned already, it's the h of x plus h of y. If x is independent of y. Remember, this is a symbol for independence. And from this result, it follows that if x and y are independent, then conditioning actually does not help. So h of x given y is actually equals to the h of x if x is independent of y. And the same thing, if h of y given x is going to be equal to h of y if x and y are independent. So knowledge of x or knowledge of y does not help the other if they are independent. So the information content remains the same. Okay, so these are important results that will help you, solving problems and doing your homework exercises. So try to make use of them whenever you have a chance. Now, I would say the last one, perhaps, in terms of entropy, is something called the relative entropy. So last idea. So relative entropy means also sometimes, if you've heard about it, maybe you will know, but some people also call this as the Kullback, Liebler, KL divergence. Right, KL divergence. So this is a very beautiful idea. It basically measures the distance between probability distributions. Nowadays, it's used a lot in machine learning applications and and loss functions, where sometimes the loss functions is in terms of the KL divergence between the source distribution and the target distribution of data. Okay, so let's say there are two distributions on the same data. So one of them is called the P of X, and the other is called Q of X. Again, these are probability distributions. So just like one of them can be a uniform distribution, the other one can be a geometric distribution or binomial distribution, things like that. So the KL divergence can be written as can be computed as DKL between P and Q. It's actually the sum over X, P of X log P of X divided by Q of X. Right, so everything is the same except changing this this fraction here. So it's relative between P and Q. If it was just P, this thing here will be the information content or entropy of X or the random variable, which in this case is X. But now we had two different distributions to describe that random variable. So we can take the ratio and compute the relative entropy. Now, important thing to note here is some properties. So first thing says that the DKL between P and Q is actually positive. So with equality only if P equals to Q. Okay, so two distributions will always be some distance, some positive distance apart, and their distance will be zero only if the two distributions are identical. That's a good property. But there's this second property which is not that great, which says it is not symmetric. Right, so that means DKL between P and Q is actually not equals to DKL between Q and P. And that's not a great property to have, because if you're looking at distances, it shouldn't matter how do you kind of order the two inputs. And the third also is that it does not satisfy triangle inequality. The triangle inequality is something that we have in traditional geometry. So if you have 3 points, A, B, and C, So by triangle inequality, you know, A plus B is always bigger than C. Actually, I should say, so these are not corner points. Basically, this is the A, this is B, and this is C. Right. So if you take the length A and then add B to it, it's always going to be bigger than this C here. That's true for all triangles. But so the DKL between P and Q, right, and DKL between some Q and R is not always bigger than DKL between P and R. Okay, so if we had 3 points PQR, PQ plus QR is not bigger than distance between P and R. So for example, let's take an example for computing so let's say, you know, the X values are between 1, 2, 3, and 4. And P of X, which is one distribution, says that, you know, for all X, we are equiprobable. That's P of X. And we have another distribution, Q of X, which says it is, you know, 1/2 if X is 1, and it's 1/6 if X is 2, 3, and 4. Right. So in other words, there is 2 different distributions. The variable is X, one is P of X. But this one says it's just 1/4 for all of them. This says it is, you know, something like this, and then this is 1/4 here, this is 1/2, this is 1/6. Okay, now if you want to compute the DKL between P and Q, it's going to be the sum over X, P of X, log 2 of Px over Qx. So it's going to be 1/4 log 2 of 1/4 divided by 1/2 plus the other 3 are the same, so we'll have 3 times 1/4 log 2 of 1/4 divided by 1/6. So it's going to be 0.189. Okay, so these two distributions are different from each other by some positive number, which is 0.189. Now, I'll just put a couple of remarks here. We're not going to go into a lot of detail on KL divergences, but I mean, the idea is useful and it's going to be used in a new concept that's called the mutual information between 2 random variables. So KL divergence how it's useful in measuring how close two distributions are. So so something called the Wasserstein distance which is used in machine learning is based on KL divergence. And the whole goal is we try to make sure that two distributions are as close as possible to each other. And therefore we make it like a loss function and then try to minimize it when we do the iterations. So these are all useful measures in information theory and other fields. But the reason why we discussed the scale divergence is because of its applicability in something called mutual information. So mutual information is actually a special case of KL divergence. Right, so why it's special? Because it assumes that QX is actually equals to is PX PY. Right, so that means that means X and Y are independent. So we'll see this example so let's revisit our case of two random variables. So consider two random variables X and Y, where h of X is the uncertainty in X before observing Y, and h of X minus h of X given Y So this is the average uncertainty reduction in X by observation or observing Y, right? So if you look at it pictorially, what you will have is, let's say we had two variables X and Y, and let's say h of X represents this circle here, right? And let's say this is this is h of Y, right? And so h of x given y is this thing here. So given y, the remaining uncertainty in x is actually h of x. So if you just shade it here, it's going to be this part. Right, so whatever is remaining in x, if you remove y, is going to be the h of x given y. And the same thing, if you look at the h of y and you remove the uncertainty due to observing x, then this will be h of y given x. That's going to be this part here. Now, something in the middle is actually the difference, right? So if you remove from h of x the conditional entropy, then you're left with this part here. Right, and this is something called the mutual information. So, so this piece here is actually the mutual information, right? So there's information content in X, there's information content in Y. What's the overlapping is called the mutual information. And actually that's computed as h of x minus h of x given y, or we'll call this as I of x colon y. So, or we can say it's h of y minus h of y given x, right? So let's see how we say this is a special case of KL divergence. So let's say the information or mutual information between x and y is actually defined as h of x minus h of x given y. And if you expand this, basically you will have the sum over small x p of x log 1 over p of x minus the double summation x and y p of xy log 1 over p of xy. That's the definition of the condition. Oops, sorry, the conditional here. So there's x, there's conditioned y. Okay, so now here what we can do is, to make them look similar, we can artificially create a y summation. So there's a summation over x already, but we can just create a summation over y. And we can say this is p of x comma y. The rest is as it is. So this is log 1 over p of x. Okay, so this is not going to change anything. It's just when you sum over y, it just goes away. And the other part is as it is. So we'll have x and y, px comma y, log of 1 over px given y. Now, now here, what you can say is, I mean, this thing here is actually pxy divided by py. right? So the denominator actually can go up, and we can replace this fraction with so we can say this is P of y divided by P of x comma y. Okay, now we can combine the summation. So I mean, if you take x and y summation common here, P of xy is common, right? So you will have log 1 over px minus log py over pxy. So this is going to be summation over x, summation over y, p of xy. And now when you subtract the log, you can actually divide them. So it's going to become log of p of xy divided by p of x, p of y. Okay. So this is an interesting expression because this is exactly the DKL between the P of X comma Y and the P of X, P of Y. Right, so if you consider X and Y were independent, and then you take the distance between the joint distribution and the product of the distributions, you actually get a distance which you can call as the mutual information, right? So it's actually so it is the or mutual is the KL distance of X and Y assuming they are in, I mean, it's the between the joint PMF of X and Y and the product of PMFs. Okay, so essentially it means how far X and Y are from independence. Okay, now some properties of mutual information before we kind of wrap up today's stuff. So properties, really there are just a couple of properties. So properties of mutual information. So the first property is, again, mutual information between any two random variables X and Y is positive. And proof is because DKL is always positive, right? So if the KL distance is positive, then mutual information, which is a special case of KL distance, is also positive. Now, second property is that mutual information is zero only if X is independent of Y. And the final property here is symmetric, which brings beauty to the whole idea. right? So IXY is actually equals to I of Y and X. So now this is a useful measure. Instead of DKL, we have something with a symmetric. So we can use it in more practical applications. So I think that's about it for our lecture today. And
Hello, sir.
yes,
Is there an example for this mutual information? Because when we derived it, this is basically what we did for the past 10 minutes was a proof, right, of mutual information.
yeah, really, yes.
And the final expression is DKL PXY is PX times PY. That's the final expression, right?
Yeah, but the thing is, you don't have to get to this route to find the mutual information. Mutual information formula is really this one. If you have two random variables, X and Y, I mean, the way to get there is this one,
Oh, okay, got it.
right? You have X, you find H of X. You have X Q, I mean, conditional distribution X given Y, you find out H of X given Y, subtract them, and then you find this region, right?
Got it. And how is there an example for this for mutual information? Because if you're gonna ask this on the quiz or something, like, is there an example for mutual information?
I actually don't have it, but you can just extend these examples, right? We had, look, we had this example, right? So I can just, so what is, let's take this example. You have H of X, you have H of X given Y. I mean, what is I? Is actually H of X minus H of X given Y, which is going to be 2.58 minus 1.66, right? I don't know what it comes out to be, but that's the mutual information. It's just a
Oh,
number.
that's it. Okay, okay, got
Yeah.
it. So you can get any problem, you get that, and then okay, got it.
Yeah, but I think what is more difficult is getting the H of X given Y. And I think that's where you should put emphasis. So maybe I can just write down a couple of steps for you to, kind of navigate through that. So, I mean, general, right? So if you have any distribution P of X, so what you can do is immediately find the H of X, because you can have the summation over I, Pi log 1 over Pi. And if you have similarly P of Y, same thing, you can just find out the H of Y. This is pretty straightforward. Or let's say Qi. Now, so if you look at P of X given Y, it's not just the values, right? Or it's not just a distribution. So it has condition. So so that means P of X given Y equals to Y is a probability distribution. Right? So I mean, it's better to say it's a random variable. And has a probability distribution. So, and this is true for all values of y. So whatever value y takes, you will have a different distribution. Now, I mean, I wish I can draw a figure like, let's say, if you have a 2D density function, right? So this is like a 2D density function. And I mean, this is the probability of x and y. This is x, this is y. So if you condition, I mean, if you condition on y, basically you will get like a slice. So you will get like, so you will get something x. This is small y. So if it's like a distribution in itself. I mean, actually, this is a continuous example, but just to illustrate the idea that you slice off the joint density, you will get like a distribution in one dimension. So the idea is use the x given y equals to y to get to h of x given y equals to y. Right, so how do you do it? You know, you kind of average over all the y's. So it's log 1 over probability right? So you have a conditional probability, just as we did here. Yeah, so that double sum the joint, and then so essentially it's just the p of y and then log of 1 over probability x given y equals to y. And then once you have h of x given y equals to y, then you can get h of x given y. The way you do it is just average over all the y's. Okay, so I think you'll get a homework to kind of practice this and understand how to compute these things.
So you have to go through all these steps starting from if you're given if you're given px and py, you have to go through all these steps of converting it to hx and hy, and then from there you have to convert to px and to hxxy, and then in the end you'll get that.
Yeah. I mean, if you're given two random variables x and y, and you're given their distributions, let's say joint distribution. So you basically can find everything. You can find the marginal, you can find the entropies, h of x, h of y. Then you need to find conditionals. And from conditional, you can find conditional entropy for a specific value of y, and then you average it, you get the conditional entropy, h of x given y. And from there, you can find the mutual information.
Okay, thank you.
Okay. All right, so I think this brings us to the end of the lecture, and I think next week we will have your project ideas. So make sure you're able to work on them and generate some selection of project that you're going to do. So all I need is a one-page description of what the idea is, what papers you've selected, what's the kind of what's the flow of your thought process. What are you going to really do in the project, like major milestones. So very basic idea, but that's due on Monday, right? And I'm probably thinking that we can have a homework instead of the quiz, because this is something that requires more. But I'll look through it. Either a homework or a quiz will be uploaded tonight, and then you will have the whole week to work on it. Also have to make it so let's see what I can come up with. Okay, so let's meet next week and talk about more, or maybe I'll give a quiz this time, and then next time we can have a better so let's say we'll have quiz 3 will be due on Monday. So next week we're going to talk about capacity of channels, so different type of channels. How do we compute the capacity and how they are related with all the entropy functions that we have talked about. So before we disperse, does anybody have any questions?
Yes. So for the quiz, it would be hard to find mutual information in those problems on there, right? Because it just takes too long to do it.
Yeah, definitely. So the whole idea is quizzes are not supposed to be very long. You will be tested on really factual knowledge.
Got it.
I
And
mean, simple stuff. I hope you've become familiar with the quizzes by now.
yes. And also it's gonna be is the same format, 10 problems in an hour? Is that the same? Will be continued?
Yeah, that's going to stay throughout the semester.
Okay, thank you.
Okay, any other question? Okay, so if not, then let's meet again next week. And hopefully by then we will have all the projects information, and we can start talking about channel capacities. Okay, then have a great week, everybody.
Thank you, you too.
Yeah, bye-bye.
Bye.